All right, so today will be lecture 13, if I'm counting correctly. I'll go ahead and share my screen here. So last time we started our discussion on estimation theory, and so we're going to be continuing that today with estimation theory part 2. I want to review kind of what we talked about before, and then we'll get into the new stuff for today. But so just as a review from last class, estimation theory is a branch of statistics that seeks to estimate the value of a random vector given a set of noisy measurements that are functionally related to the random variable or random vector of interest. So that's starting to kind of sound like the definition of navigation, right? Navigation is estimating, not necessarily determining, because we don't know for sure, but we can estimate the position, velocity, and attitude of a spacecraft given available measurements of its surroundings. And so estimation theory is basically going to be the tool, the mathematical framework for most of the rest of the work that we do. So words like covariance and expected value and measurement sensitivity matrix and measurement covariance matrix, those are going to be our friends for the rest of the semester in one way or another. So we talked about how a linear measurement model, which is how we're going to start, a nice simple linear measurement model. We have a perfect measurement, which is some function of the state. And in this case, it's a linear function of the state. It's simply some h being multiplied by the state, where h is some matrix. We know that really there's noise, so we can model noise as some random variable, which is a Gaussian zero mean white noise with a standard deviation of sigma I in this case. We know that we can stack these into a matrix. And so then the question becomes, how do we solve a problem that looks like this? So I have y, which is our measurement matrix, or measurement vector. The little vector kind of cap shows us that it's a vector. And then the squiggle above that, or the tilde above that, is to let us know that it is noisy. Noisy measurements. So this is the sort of thing that we get out of our sensor, is h times our state plus some vector of noise. So this looks a little bit like just ax equals b, right? It's kind of that same basic sort of problem. And I asked, how do we solve a problem that looks like this? This measurement is equal to some linear function of our state and some noise. And so two possibilities that we can consider. One is to ignore the noise and just say x is equal to h inverse y. Problem is h is not invertible. However, you can take what's called the Moore-Penrose pseudo-inverse and say, okay, x is h pseudo-inverse y. That's one option. Another option is what we call least squares, which least squares, I think most people have seen least squares before. The idea behind least squares is y, we're going to treat y as some vector, in which in this case it's orange, floating around in this example in 3D space. And h1 and h2, which are the columns of the measurement sensitivity matrix H, are also floating around in 3D space. And those two vectors form a plane, as any two vectors do. And that plane does not include y. It's actually not possible to find a spot on the h1, h2 plane that matches y. But we can find a spot on the h1, h2 plane that best matches y. And I think of that as sort of like the blue shadow that the orange vector casts on the h1, h2 plane. And so that's what we do. We get to command x1 and x2 in this particular kind of two-dimensional or three-dimensional case. We can command the elements of the state to best approximate the measurements. And that's essentially what we're doing. And if we treat this as a geometry problem and we solve the geometry problem, we get what ought to be a familiar equation for those of you that have seen least squares before. Our best estimate of x, which is why it has the little star superscript, is h transpose h inverse h transpose y, which, incidentally, this is the pseudo-inverse. So the original method that we talked about, x is equal to h pseudo-inverse y here, is exactly this. They're the same thing. And the idea behind least squares is that we are trying to minimize the sum of the squared error residuals, and that's where we get the word least squares. So in this case, I set this up as a geometry problem, just because if your brain works the way mine does, this kind of clicks a little bit better, like understanding what least squares is trying to do. You know, we're working with some solution space that doesn't include the vector we're trying to match, so we're trying to minimize our residual because that's the best we have. That makes more intuitive sense to me, but you could also approach this exact same problem using the techniques of optimization. And so if you've taken Dr. Hickens' design optimization course, that covers some very similar topics. I borrowed his notation of X star for the optimal solution. And so actually today we are going to use optimization techniques to explore the cooler older brother to least squares, and then the even cooler, even older brother to least squares. And that's kind of the minimum that I'm hoping to get through today. And if we can accomplish both of those, then the next topic I want to discuss is something called batch estimation, which, if you've read ahead, is going to be necessary for the first problem on homework 2. So anyway, we're going to start today's material, but any questions about any of this review before we get into the new stuff? All right, groovy. Let's get into it. So estimation theory part 2, we're going to start with the cooler older brother to least squares, which is called weighted least squares. Weighted least squares. So, and we're going to abbreviate this because we don't have all day to be writing this out. WLS, weighted least squares. So there is a shortcoming of the least squares approach. LS is least squares. Is that it treats all measurements equally. And so there's a problem there. So if we look at the equation for least squares, we have this measurement sensitivity matrix H, which describes a relationship between Y and X. But there's nothing in there modulating that some of our measurements are maybe better than others. Some of our measurements are more trustworthy than others. Some of our sensors are a little bit more noisy than others. Some of our, the nature of our estimates are different than others. So we could consider, suppose some measurements carry more uncertainty than others. Or suppose measurements are not all of the same type. Suppose measurements have vastly different units. Or one example I would give is, and we haven't quite made it to triangulation yet, but suppose you are trying to triangulate the location of a spacecraft that's here, and you know the apparent direction to the Earth, which is right next to you, and then you also know the apparent direction to Saturn. And you know that there's going to be a little bit of uncertainty in your measurements. So really there's some cone that you know contains the Earth. And then there's some cone that you know contains Saturn. And even if you have the same uncertainty in your unit vector, just the distance of Saturn makes us much more likely to want to trust Earth and not Saturn. And so that's kind of an example of, so actually we will at some point get into a method of triangulation where if we know that some of our waypoints are much, much further away than others, we will want to differentially trust the waypoints that are closer versus the one that are further away. And so we'll talk about that. And that uses something called weighted least squares. So attempting to use regular least squares, and this is going to be a huge shocker, with a weighting matrix gives us weighted least squares. So attempting to is the weighted least squares, or WLS approach. And so we will start with a problem that looks like this. So this is our kind of problem setup. So we've got our measurement vector, all of our measurements stacked, and we appreciate that there is noise on that. And that is going to be equal to some measurement sensitivity matrix times our state, plus some vector of noise, where this is the Greek letter nu, written like so, and not the letter V. I just want to be clear about that. Nu as in it's the letter N from the Greek alphabet, and we're using it for noise. So we will begin solving weighted least squares with an optimization problem. So this is the method that we did not explore in the last lecture, and we're going to see it explored here. We begin by setting up an unconstrained optimization problem. Okay, so for those of you that have taken design optimization or some method of optimization before, which was my case, I took that class before I took a navigation course. This is going to be smooth as butter. You've seen this before. This is pretty straightforward. For those of you that have not taken optimization, most of this should make sense because a lot of design optimization and kind of optimization in general, well, I should be clear, it gets pretty spicy. But most of the basic optimization is kind of an extension of what you learned in calculus, right? Trying to find the maximum value of a function. And so we will, actually, you know what? Let me write out the next equation, and then I'll ask somebody who hasn't taken design optimization how they would solve it, because I'm going to guess that you can intuit the solution. So the problem looks like this. We have some function, which we're going to call our cost function, j of x, and it's equal to what? Well, it's going to be our residual, so y minus hx, but we want it to be our residual as a scalar, and we also want it to be our residual squared, because what we're about to do is we're about to try to minimize this function. And if you're minimizing a function that can go negative, you could just go arbitrarily small. So we want to force it to be a positive value. And so one way we would do this is we would say, oh, well, let's just take this, which is a vector, and dot it with itself. So y minus hx. Don't write this, by the way. Don't write what I'm writing because I'm about to erase this. And then a 1/2 out front. If we solve this problem, we would get this solution from last time. This is another way of getting to that solution. What we're not going to do is that we're going to introduce one additional step. Apologies if you already wrote that out. Just make a little bit of room. We're going to fit in the letter W and then y minus hx. Okay, W is a symmetric weighting matrix, and it's typically going to be diagonal. So where W is a symmetric, typically diagonal. In fact, I've only ever seen it diagonal. Weighting matrix. So this is where you, the operator, can choose to tune. Okay, we want the weight on the first measurement to be twice the weight on the second measurement because we trust it twice as much. This is kind of your tuning parameters, right? So now I'm curious. I want to take a volunteer who has not taken design optimization before, and I'm curious what technique you might use to solve something like this. Ooh, maybe that was a very spicy question to start us off with. All right, I'll also open the floor to people who have taken design optimization. How do we solve a problem of this type?
Could you iterate through your variables and do basically a sensitivity analysis?
Ooh, okay, I like the idea. I like sensitivity analysis. However, there is, in general, if there is a non-iterative way to solve a problem, that's the preferred way to solve the problem. So you're not wrong, but there's a better way. Do you want to try a second time?
If you can manage to find an inverse, then that'll make your life much easier.
Okay, I like that idea too. Inverse is a great tool. We want to do something ever so slightly different. Let me start with something much simpler. Let's just take y is equal to h of x. Or actually, let's not do that. Let's these letters are going to get us confused. Let's just take a nice scalar problem that looks like j is equal to f of x. Okay, j is some function, or j is the output, f is the name of the function, right? Find the minimum of j. So this is the minimum of a function. So we don't necessarily need the inverse, but there's another trick that we might have learned in calculus that helps us find the minimum of a function.
It's solve for the first derivative is 0 and the second derivative is positive.
That is exactly it. So if you want the minimum, very good job. The minimum of a function requires that the first derivative is 0 and that the second derivative is positive. Now, if you know that your problem is convex, you don't really need the second check because, like, you know it's going to be a minimum and not a maximum. If you want it to be extra fancy, you can go through and, oh, let's make sure it's a maximum, not a minimum. So that's a technique from calculus. I'm guessing that not a ton of folks have taken design op, or I hope you do. I certainly hope that if you have time for it before you graduate. It's a great course, very, very worth your time. What I want to make intuitive sense to you right here, because this is about to get a tiny bit spicy, is that we are literally just taking the derivative and setting it equal to 0. However, because design optimization is fancy and we all are very highly educated, we now need to call it the first differential condition. But that's what we're doing. We're taking the derivative, setting it equal to 0. So to solve, it's important to me that everybody gets why we're doing that before we move on. To solve, we apply the first differential condition. And that is that the derivative of j, which is a function of x, with respect to x is equal to 0. Oh my goodness. This is matrix vector calculus. This is why Paul wanted you to know how to do matrix vector calculus. Matrix vector calculus. Yep, we found a use case for it. This is why we had to go through that lecture, because now we're about to take the derivative of a function with respect, which is a function of a vector with respect to a vector. So let's make our lives easy. First, I'm going to rewrite the original function. So right now it looks like min j of x, and all I'm going to do is expand everything. So I'm going to write this as 1/2, let's see. So this is a little bit like FOIL from like high school algebra, right? It's like the first times the first, and then the outer, and then the inner, and then the last, right? So this is going to look like y transpose wy, there's our first term, minus 2y, oh, I think I have a mistake in my notes here. Pardon me. There's a lot of vector math coming today, so I want to make sure we don't make any silly mistakes. This should be transposed. And then WHX, X gets a hat, plus X transpose H transpose WHX. Okay. So stop me if you disagree with me. What I'm saying is that this equation, let me go sky blue here, is the same. This is not different. I'm just expanding terms. Okay. Now it's about to get a little bit easier. Well, I should say, this is now going to be easier to take the derivative. So we're going to do this term by term, right? So what is the derivative? We're going to do term by term. Remember our matrix vector calculus. Okay. So it's going to be 1/2, open parentheses. So somebody who's feeling brave, and we're going to do this together. What is the derivative of y transpose wy with respect to the vector x?
Is it just 0?
It is, very good. So if x isn't there, it's just 0. Same idea as regular calculus. Excellent. All right, now I'm going to cycle it out because I want to do some teamwork. So somebody else is going to help me with the second term. What is the derivative of 2y transpose whx with respect to x?
It'll be 2y transpose wh.
Yep, you just drop x. Very nice. See, I was worried that y'all weren't going to catch on to the matrix vector calculus. I am very pleased so far. Okay, now the hardest one. Somebody else. What is the derivative of x transpose h transpose whx with respect to x?
It's 2x transpose h transpose wh.
Excellent. Oh, I'm so happy. Very, very good. Oh, wait, hang on. You said it, and then I was like going way too fast. Very good. 2x transpose h transpose w h. So all we do is we drop the trailing x and we put a 2 out front, right? Because we know that x transpose ax, if you take the derivative, is 2x transpose a. You drop the trailing x, 2 goes out front, which is analogous to ax squared becomes 2ax in scalar land, right? So we remember our matrix vector calculus. Excellent. All right, so now we can start to simplify. And all of this we said is equal to 0, right? From over the other side of the equal sign. So what I'm saying is x transpose h transpose wh is equal to y transpose wh. Okay, let me know if you agree or disagree with that. Hopefully that's reasonable. Just skipping one step. Then the next is I'd really like x to be on the right. So what I'm going to do is transpose both sides. And so what that's going to give me is you change the order and then you apply the transpose differently. So this would be h transpose w, but remember w is symmetric. And so if we transpose it, we get w again. And then h and then x. So h transpose whx is equal to h transpose w y. Okay, just changing the order. That's how we apply our transpose. Finally, I'm going to multiply the left side by the inverse of itself. And so what we get, oh my goodness, this is starting to look familiar, is h transpose wh inverse h transpose wy. And that is our equation for weighted least squares. You'll notice it looks an awful lot like the equation for regular least squares, but with a w shoehorned in there twice. So this is our WLS equation. And so hopefully you see that we could have used a similar tactic to achieve the original least squares equations. If we just left w out of it, it would have simplified to h transpose h inverse h transpose y. Okay, so, and I'll make a note here that w is equal to w transpose, in case you're reading the notes later and you're confused why we skipped that step. We'll leave that there. Okay, excellent. So questions on our weighted least squares equation. Otherwise, we get to discuss something even more fun, which is whether or not we have a biased estimator. So far, so good. Questions on the matrix vector calculus and the design optimization techniques? All right, either I'm really good at explaining things or everybody's terrified. So it's really, really good or really bad. Let's keep moving. So here's a question. What is the expected value of, oh, I should be clear. This is our optimal estimate. Sorry, apologies. What is the expected value of our optimal estimate? Well, we can answer that. So the expected value of our kind of best guess is equal to the expected value of, okay, let's think about this now. It's H transpose WH inverse H transpose WY. But remember that Y with the squiggle on top is equal to HX plus nu. So we're going to go ahead and do this. We'll see how this is going to go in a second here. So actually, I'm going to do it this way. I think this is going to make a little bit more sense. This is the expected value of H transpose WH inverse H transpose W, and then in parentheses, Y plus nu. Okay, I'm running out of space on the right side, so maybe I can kind of cheat a little bit. Just gonna scooch all this over. Am I allowed to do that? Yeah. There we go. Okay, so I just lost the dot, my question mark here. All right. So all I'm saying is that y with the tilde, so the noisy measurement, is a theoretical perfect measurement plus some noise. So we're just splitting that up. Okay. So now we remember our expected value operator, right? We can distribute this. So first of all, the interior of the expected value should distribute to H transpose WH inverse H transpose WY plus H transpose WH inverse H transpose W nu. And then also, we remember that the expected value operator can basically skip things that aren't stochastic. So we can kind of do two steps in one here. I'm going to say this is equal to H transpose WH inverse H transpose W, and then we have the expected value of Y, okay? And then plus H transpose WH inverse H transpose W expected value of nu. Okay, so somebody remind me, Y is our perfect measurement, right? It is a theoretical thing that we never actually get to interact with, but mathematically, it is our measurement if there were no noise. So, and it's not a random variable, it's just itself. So what is the expected value of Y in that case? Or let me say that a different way. If Y is not a random variable, we know that the expected value of just, I don't know, the number 2 is 2, right? The expected value operator leaves things alone if they're not stochastic, right? The expected value of Y is just itself, okay? But not so for the expected value of nu. Remember that nu, which is our noise vector, is a random variable, and we've actually already said what its expected value was, and that is, oh, maybe that was in the last lecture. Nu is zero mean Gaussian white noise, zero mean. It is distributed as having zero mean. That's what this notation is saying here. As a vector, it has a mean of 0, which would be a vector 0 rather than a scalar 0, and then a covariance of R. That's our measurement covariance matrix. But what so that means is that the expected value of nu is 0. So we're not expecting our noise to be anything other than 0. It might be something, but on average, it averages out to 0. So we can say that the expected value of X star is equal to H transpose WH inverse H transpose WY. Okay. But then here's what I'm going to say. Isn't Y just equal to HX? So this is really H transpose WH, going to be a lot of that today, inverse H transpose WH X. So far, so good. However, what do we notice? H transpose WH inverse H transpose WH cancels out. So the expected value of X star is X. So let me just kind of rewrite this over here. The expected value of X star is X. As a reminder, X is the true state. So the on average, this is what it's saying, on average, our best guess equals the true state. It won't in practice, but on average it will. If we did this 10,000 times, it would average out to the true state. Okay, so what this means, kind of more mathematically, is if our noise is unbiased, unbiased meaning zero mean. Then the expected value of our optimal estimate is the true state. Thus, what we have here is called an unbiased estimator. We're going to get the wrong answer because we have noisy measurements, but we're going to get something that's close to the right answer. And we're going to get something where if we did this many, many times, we would not be consistently off by the same amount, right? If you were consistently off by the same amount, if your error was non-zero on average, this would be said to be a biased estimator, meaning that not only are we wrong, but we're actually adding in some noise, which is saying, oh, well, we always seem to be off by 2 for some reason, right? That would be a biased estimator. All right, that's neat. We have another question we might want to answer, but this is another little checkpoint where we can pause and answer any questions. Hopefully people are getting a little bit more comfortable with the expected value operator and a little bit more comfortable with matrix vector calculus because there's plenty more of that today. But questions up to this point or keep on moving? All right, we're going to keep moving. So next we're going to talk about covariance. So as a reminder, we didn't already say this before, I believe we've said this before, but here it is. The covariance of the state is defined as P, which is the expected value of X star minus the expected value of X star, X star minus the expected value of X star. Wait, that's a bracket, then it's parentheses, then it's transpose, and then it's bracket again. Okay, it gets a bit confusing. This bracket goes with this bracket, this parentheses goes with this parentheses, this bracket goes with this bracket. So it's X minus its average value times X minus its average value transposed, all of that expected value. That is the definition of the covariance of the state, right? And that's true for just any random variable, right? The expected value of that random variable minus its own expected value, all of that times itself transposed, and the expected value of that gets you your covariance. And so what that means is we can plug in some information, some equations that we have for X star and for its own expected value, and actually derive an equation which can give us our uncertainty, our covariance matrix, as a function of the kind of tools that we've been using to solve for X. Because as we move forward in this class, it's going to be not good enough to say, here's our state. We need to start saying, here's our state and here's how sure I am, right? That's where the estimation theory comes in. So let's just tidy things up for a little bit here. So we just said that the expected value of X star is the state. Okay, so what I'm going to say then is the expected value, there's a reason why we did this in this order. Oh, sorry, already screwed up. X, so our optimal estimate minus its own expected value is equal to our optimal estimate minus the true state, which ought to basically just be some noise, right? So what this is H transpose W H inverse H transpose W Y plus nu minus H transpose W H inverse H transpose W Y. And so we see that the difference between these is X star minus X. The difference is basically a bunch of stuff happening to the noise because the measurement cancels out of this. So we get H transpose WH inverse H transpose W nu, where nu is our noise. Okay, so then the expected value of this times this transpose is our covariance. So P is equal to the expected value of, big bracket, because here comes a lot of stuff, H transpose W H inverse H transpose W nu, and then it's all of that transposed, right? So then it's going to be nu transpose W H H transpose W H inverse. This should really be negative T, but we end up with something symmetric, so the transpose doesn't matter. Okay. This is ugly. Hopefully it makes sense how we got to this step, right? All we did was we took this and so this is this part. And then here it is again transposed. And as a reminder, right? A, B transpose is equal to B transpose A transpose, right? Just as a reminder. So that's how we arrived at this. So let's try simplifying. One of my favorite things about the expected value operator is it skips over everything that isn't a random vector, right? So this is going to become P is equal to H transpose W, H inverse H transpose W, expected value of nu transpose W H transpose W H inverse. Okay, now expected value of nu transpose. Have we seen that before? That is the definition of R, our measurement covariance matrix, which we're going to assume that we know. And so therefore, P is equal to, here it comes, H transpose W H inverse H transpose W R W H H transpose W H inverse. And this is our weighted least squares covariance equation. You'll notice that it has nothing to do with the state. You don't need to know the state to know how certain or uncertain you are. You need to know things about your measurement sensitivity matrix. You need to know things about the mathematical model that you're using to estimate your state. But this is our weighted least squares covariance equation. All right. So, cool stuff. That is the end of our discussion of weighted least squares. It's a great natural pausing point if anybody has any questions. Otherwise, we're going to get into our discussion of maximum likelihood estimation. And I think we will take a break after our maximum likelihood estimation equation. We certainly will have earned one by then because there's going to be plenty of math. But questions on weighted least squares? So far, so good? All right, going to keep on moving then. So we said before at the top of the lecture that weighted least squares is essentially the cooler older brother of least squares. Oh, it looks like I'm going off the edge of the page here. Hopefully this turns into a decent looking PDF. So then there's an even cooler, even older brother, which is definitely what I would recommend using and what you will be asked to use in homework 2, which is called maximum likelihood estimation. Okay. So if least squares is, what is it, Charmander, and weighted least squares is Charmeleon, then maximum likelihood estimation is Charizard. This is the full evolution. This is as good as it gets, right? And the idea is basically this. Is there an optimal weighting matrix which gives us the best possible chance, the maximum likelihood of getting a good estimate? That's the idea. So we're not fundamentally changing anything about weighted least squares. We're just replacing W with the theoretical perfect weighting matrix. That's the idea. And so once you hear that, you go, why would I ever go back to weighted least squares? It is so much better. There are reasons why algorithmically you might choose weighted least squares, especially depending on how difficult it is to come up with your optimal weighting matrix. Sometimes it's better just to come up with your own. It might be faster computationally, but from a theoretical standpoint, MLE is always going to outperform weighted least squares and regular least squares. This is the full evolution, right? This is Charizard. So maximum, here comes the definition. Maximum likelihood estimation is an extension, is an extension of the least squares approach which applies a weight to each measurement as determined by the measurement covariance matrix R. So it turns out that R, which is our measurement covariance matrix, is, and I think we're going to show this. I believe we're heading in that direction. Essentially, we're moving in the direction of showing that R inverse is the theoretical best weighting matrix that we could possibly use, which is great because we're not introducing a new character here. So we're going to start with our kind of top level, nice and simple. Y is equal to hx plus nu, where, as a reminder, nu, our noise vector, is a random vector which is distributed as a Gaussian, having zero mean and a covariance of R, our measurement covariance matrix. Okay, so our expected value of Y is equal to the expected value of hx plus nu. But we know that h and x are not random, only nu is random. So this is equal to hx plus the expected value of nu. But we just see right here, the expected value of nu is 0. On average, there's no noise, right? The noise is non-biased, zero mean. So what that is to say is that the expected value of the noisy measurements is the true measurements, which we never get to interact with. We only ever see the noisy measurements. Okay, so the reason I say that is to say that Y with the noise minus its own expected value is just nu. That's the idea. And so the expected value of our measurement, or so the measurement covariance, the expected value of Y minus its own expected value times Y minus its own expected value, bracket, close parentheses, transpose, bracket, is equal to just the expected value of nu transpose, which is R. So the same matrix R, this measurement, this is really a noise covariance matrix. The noise of the, or sorry, it's the measurement, getting ahead of myself. It is the covariance matrix that describes the distribution of the noise that we're applying in our mathematical measurement model. So this is the measurement covariance matrix. But we'll see that it's the exact same matrix that describes the covariance of the measurement itself. So that's kind of where it gets its name. So this R is saying this is our uncertainty in our measurements because this is the amount of noise that we're assuming that there is in the system. That's the idea. Okay, so this is going to come to help us in a minute. So because, let's see here, because nu is a Gaussian random vector, so is y. If you add Gaussian noise to something that doesn't have any noise, then we can treat that as also being Gaussian distributed. Therefore, we can quantify its probability density function. We can quantify its PDF. Okay? So the probability, I'm going to leave a lot of room here. Probability of y is equal to, and this is just from the definition of a Gaussian distribution, right? It's going to be 2 pi to the value m over 2, where we're assuming that there are m measurements, as in Mike. Determinant of r to the 1/2 power times the exponential function of negative 1/2 y minus expected value of y. Sorry, that's a bracket. Transpose r inverse y minus the expected value of y. And then this is our bracket. There we are. And as a reminder, the expected value of y is just y, which is the same thing as hx, right? So this is the equation that lets us characterize the probability of our measurement. So this is the PDF of the measurement vector, okay? So what we can say then is the probability, this is where we get into almost like a Bayesian situation here. The probability of y given x is written as p of y given x is equal to, we're going to have just this whole coefficient out front. I'm going to call this c equal to c. Probability of y given x is just c times the exponential of negative 1/2 y with the noise on it minus hx transpose r inverse y minus hx. Okay. So this is the probability of y given x. Now, the reason that we take the time to write this out is we want to find a value of x that maximizes this probability. So we're saying we're trying to maximize the likelihood that our estimated state caused the given measurement. So I'm going to write that out. Our goal, now that we have this equation, is to find x star that maximizes the probability of y given x. Actually, that should have a star on it. Okay. So we want to maximize that, which is to say, this is just the likelihood that x caused y. So we have a set of measurements. We're looking for the state that maximizes this conditional probability. We're saying, what is the state that gives us the best chance that this is the state that caused the measurements? And so this is a optimization problem again. So this is a maximization problem instead of a minimization problem. We're going to say max j of x is c exponential negative 1/2 y with the noise on it minus hx transpose r inverse y minus hx. That's what we're trying to maximize. Now, first, I mean, this is a lot. This is pretty spicy. We're going to simplify this. We're going to observe, OneNote's getting a little upset with me here. We'll give OneNote a minute to collect its breath, and I might need to kind of save and restart. The next several steps are going to be simplifying this math problem until eventually we get to a matrix vector calculus problem, and then eventually we get to an optimization problem, and then we ultimately solve for our MLE solution here. So just bear with me. This looks pretty ugly, and if you'd asked me how to solve this, I don't know if I could do it, but we're about to employ some steps that are going to make this a little bit simpler. So first, observe that maximizing the probability, the conditional probability of y given x is the same as maximizing. Wow, we're just going to try again with that word maximizing. I can do better than that. I know my handwriting is not the best, but I can do better. The natural logarithm of the conditional probability of y given x. Wow, so we've got optimization, matrix vector calculus, we've got Bayesian conditional probabilities, Gaussians, and now we also have logarithms. This is definitely getting into the spicy math side of things. So we're going to take the logarithm. So the new j of x, maybe this should really be like j prime x, is equal to the natural log of c minus 1/2 y minus h x transpose r inverse y minus hx. See, whoever said that logarithms were nasty? Logarithms are there to make our lives easier. So what we observe, well, first of all, now I'm going to rewrite this as a minimization problem, just because most of the tools that we have in optimization work better for minimizing. We're just going to change the signs. This is negative ln c plus 1/2 y minus hx transpose r inverse y minus hx. Okay. Now, this first term, ln c, has nothing to do with x, right? This is the same thing as like a vertical offset on your function, right? It will change the actual maximum or minimum value, but it won't change the location of the maximum or minimum value. So this has nothing to do with our state. Therefore, it's okay to drop. So I'm going to introduce yet another problem, which looks like this. The minimum of j double prime of x, we're just saying, all right, this is a different but equivalent optimization problem. And now it's just the minimum of 1/2 y minus hx transpose r inverse y minus hx. Okay, now I'm going to expand this a little bit, and then we are careening towards a matrix vector calculus problem. So bear with me. The minimum of j double prime of x is equal to 1/2, and then we're going to open the parentheses, y transpose r inverse y. This is looking a little familiar. Minus 2y transpose r inverse hx plus x transpose h transpose r inverse hx. Okay? Then we will apply the first differential condition. Which is to say that the derivative of j double prime of x with respect to x is equal to 0. So here we go. What is the second derivative of j of x with respect to x? So we'll do it one term at a time, and I'm looking for volunteers who didn't help me with the weighted least squares solution. So what is the derivative of y transpose ry with respect to x? This is the easy one.
That one's just 0.
Just 0, very good. And then next, what is the derivative of 2y transpose r inverse hx with respect to x? What happens then?
Just drop the x.
Just drop the x. Love to hear it. Okay. 2y transpose r inverse h, and the x just drops. Finally, we get to the tricky one. What is the derivative of x transpose h transpose r inverse hx with respect to x?
It's 2x transpose h transpose r inverse h.
Very good. Excellent. So we have a 2 out front now because we've dropped an x. This is essentially x squared going to 2x, right? So we have 2x transpose h transpose r inverse h. Boom, we're good. Okay, this is starting to look real familiar. Cancel, cancel, cancel. What we get out of this is y transpose r inverse h is equal to x transpose h transpose r inverse h. And you might have already caught on to the punchline that r inverse is everywhere that a w used to be when we were doing the weighted least squares problem. So I'm going to clean this up a tiny bit. This can be rearranged to say h transpose r. This should really be r inverse transpose, like to the power negative t, but because it's symmetric, we can get away with this. The y is now on the right-hand side, and this is equal to h transpose r inverse h x, right? And so now we're going to multiply both sides by h transpose r inverse h, quantity inverse, and that's going to give us that x star is equal to h transpose r inverse h inverse h transpose r inverse y. And there it is, shockingly familiar to our weighted least squares equations. And this is our maximum likelihood estimation equation. So if we have the measurement covariance matrix R, this is the theoretical best possible guess for X that we can put together. Now, this is still limited by the fidelity of our measurement model and so on and so forth, but this is basically as good as we can do. So, yeah, essentially we're just this is basically the point here, simply use R inverse as your weighting matrix. That's kind of the punchline here. So that was a bunch of math. Y'all have absolutely earned a break. So why don't we take a break? I'm going to stick around for 5 minutes to answer questions, but otherwise y'all are free to take a bathroom break, get a drink of water, whatever you need to do. It's almost 5:03, or sorry, 7:03 for you. I'm subtracting versus adding. So let's say back at 7:08. And then we will discuss covariance, which is actually pretty straightforward. And we'll even have time to start batch estimation. So you should be able to get pretty far through your homework after today's lecture. But yeah, go ahead and take a break. right, reckon it's time to get back into it. Hope everybody's feeling good. I'm going to keep this math train rolling and wrap up our discussion of MLE, and then we'll get into batch estimation. So we'll just see how far we can push it today. Let's see what we can do. Of course, I want to let you out of here at a reasonable time. All right, so we've achieved our equation for x, but of course we know that in this class that's not good enough. We need to go back and discuss how sure we are, right? So we can again the state covariance matrix P, which, as a reminder, just to write it out again, is equal to our optimum estimate minus its own expected value times that, again, transpose. All right. So as a reminder, recall, because we kind of did a lot of the hard work before with the weighted least squares, that the expected value, I'm getting a little spinning wheel here. I think OneNote might be getting mad at me. Too much math in one day, it says. All right. But essentially what we're going to be doing next is following some similar steps that we did with the weighted least squares, but with R inverse wherever W used to be. And we'll be able to skip a couple of steps because we've kind of done the hard work already. And actually, the P matrix is going to work out to be delightfully simple when we're done compared to what you might expect otherwise. All right. I don't love that it just says recall that. I was kind of hoping that everything else. All right. I'm just going to close out of OneNote, open it back up. Bear with me. There we go. All right. Sometimes that does it. Recall that the expected value of x star is equal to x, and that x star minus x. So our estimate minus the true state would in this case be, from our discussion before, H transpose R inverse H inverse H transpose R inverse nu, where nu is our noise. Okay. So from that, we know that P is the expected value of all of this times all of this transpose. That's essentially what we're going to be doing now. So this would be, here we go, H transpose R inverse H inverse H transpose R inverse nu, nu transpose R inverse H, H transpose R inverse H inverse. That's a mouthful. All right. So our next step is the expected value operator really only cares about the things that are stochastic. So actually, this simplifies quite a bit to P is equal to H transpose R inverse H inverse H transpose R inverse expected value of nu transpose R inverse H transpose R inverse H inverse. See, if I just had these equations up on a screen and said take notes, I'd feel bad, but like I'm writing it too, so my hand's also cramping. So we're all in this together. So finally, well, not finally, there's two more steps. Isn't the expected value of the noise times the noise transpose just R? So this is going to simplify quite a bit, actually. So in a moment, when I regain my ability to scroll with my mouse wheel, there we are. State covariance is H transpose R inverse H inverse H transpose R inverse R inverse H transpose R inverse H. I'm liable to fall asleep just writing it. Okay, so here's the fun part. R inverse R or R inverse, either way, that's just the identity matrix, which we can leave out of our math, right? If you're doing R to something and then you're undoing R, or if you're undoing R and then you're doing R, cancels out. So that simplifies. This is, it's so much fun when things start to simplify. It's so satisfying. So now we get H transpose R inverse H transpose R inverse H transpose R inverse H inverse. And what you'll notice is that this or the other one, you can kind of pick the first two or the last two, also cancels out. So our state covariance matrix is H transpose R inverse H inverse, which is delightfully short and sweet compared to all the math that it took to get this far. And actually, what's even cooler about this, so this is our MLE covariance equation, should look a little familiar because when we computed X, it was H transpose R inverse H transpose R inverse Y. So you can just borrow whatever line of code that you wrote to find that and then just delete everything after H transpose R inverse Y. Or you can compute the covariance and then save that and use it as the first step when you're computing your X star. So they're nice and kind of neatly linked compared to if we go back up to P for the weighted least squares case, it's kind of its own thing and it's related, but kind of ugly. So it's nice and simple by comparison. And there we have it. So we have now, just as a reminder, kind of what we've accomplished. This is least squares, which is kind of our basic version of trying to solve a noisy linear state estimation problem. Least squares is a great way of doing it. Kind of minimizes our chance of being wrong or gives us the best possible answer. Weighted least squares is better because it actually provides kind of preferential treatment to measurements that we know are more trustworthy than others. And if you take that idea to its logical extreme, you get maximum likelihood estimation, which gives us the absolute best case weighting matrix that we could use. So it's the king of all weighted least squares is MLE. And there we have it. So those are three different methods, which will all be covered in homework 2 of solving a linear state estimation problem. And our next topic is something which I would cover next time, but I want to at least introduce today because you will need this for problem 1 of your homework assignment. And actually, we won't get to it today. I'm probably going to go at least until the bottom of the hour because I really want to get into an introduction to batch estimation. There is an example that we'll get to next time on Monday, which we'll have an announcement about that, where it's very similar to homework 2 problem 1. So it's going to be very helpful for those of you that are a little bit lost with homework 2 problem 1. All right. So questions before we move on? Otherwise, it is time for batch estimation. So we'll start batch estimation. There we are. So here's the situation. We've been solving problems that look like this. Y is equal to hx plus nu, right? Our measurements are equal to some linear matrix, linear matrix times our state plus some noise. The thing is, this assumes that all of our measurements come in at the same time, which they rarely do. Right? Measurements are rarely available at the same time. And then we're faced with a problem because now we're not measuring the same thing, right? Let's say you measure the state of your spacecraft and then 10 minutes later you get another measurement of the state of your spacecraft and then 10 minutes later you get another measurement of the state of your spacecraft. Now you have 3 measurements. And you might be thinking to yourself, oh good, we have 3 measurements, now I can try to solve for the state. But the thing is, you're not measuring the same thing. The state changed in between your measurements, right? So we need some sort of trick, some sort of technique that we could use if we want to use our measurements in a batch estimation to say, well, let's somehow try to observe the state at a specific time using measurements of the state at some other time, which seems kind of chaotic and weird, but actually we have some mathematical techniques that we can use to do that. So I hope that makes sense. I'm going to draw a picture in a second, which might make that make a little bit more sense. So in practice, measurements are often available periodically. There we are. So we have a couple of options. One is to have a computer constantly running that will process each new measurement as it comes in. So we can process as they come in. This is called sequential estimation because it happens in a sequence. And the king of sequential estimators is something called a Kalman filter, which we have an entire unit about Kalman filters. Going to be 4 or 5 lectures about Kalman filters later in this course. Another option is to save your measurements until you have enough and then process them all at once, kind of after the fact. And that is referred to as batch estimation. Throw them in the oven and wait. We're making a batch of cookies. That's the idea. So here's the problem, right? Let's say we've got, I'm trying to think, I actually don't have a picture in my notes for this, so I think we're just going to kind of freestyle on this one. But let's say we've got a spacecraft. Yeah, okay, here we go. We're doing this live, so I'm making this up as we go. Bear with me. Here's the Earth. Here is a spacecraft. And it is orbiting. So I guess I'm kind of borrowing one of my diagrams from orbit determination. And now it's over here. And let's say we can measure the distances. Well, I basically did just borrow my diagram from orbit determination, right? So let's say that the spacecraft has some state at time t1 and some other state at time t2 and some other state at time t3. And we've got some measurement, which we're going to call y1, and some measurement y2, and some measurement y3. And the problem is you are not measuring the same state. So we need some way to use measurements of x at ti to estimate x at tj. That's my point. Where I and j don't necessarily matter, but we need to be able to use measurements at some time to estimate the state at some other time. And that is completely impossible unless we also have a model. So we don't just need a model describing the relationship between the state and the measurement. We also need a model describing the relationship between the state and the future state. And now we can use those things together to say, okay, I estimated the state a while ago, and I think that the state progressed like this. Therefore, here's my best guess of the current state. And you can do that for each of the different measurements. You can map your measurements onto the same time, and that is batch estimation. That's essentially what we're going to be getting into. And there's a fun technique that we can use to map the state from one time to another, which we will discuss before we get to the end of this page of notes. So buckle up and bear with me here. So suppose we have, you know what? I'm going to use the letter M. In my notes, I use N, but I'd like to use M. M measurements, because I like to use N for the number of states, collected at M times. These are all different times. So if we write that out, it would look like this. Y T1 is equal to H1X T1 plus new 1. Actually, you know what? That's going to be, this is a scalar, right? This is a scalar measurement of X. And then Y with the squiggle, but not the vector. This is a scalar measurement. T2 is equal to H2 X at T2 plus mu 2, and then all the way down to Y at T mic is equal to H mic X of T mic plus mu mic. All right, so for brevity, we're going to make an abbreviation because this is getting to be a lot. For brevity, we will abbreviate. And I just want to make a note. I was today years old when I realized that the word abbreviate is based on the word brevity. I didn't connect that. So that's kind of cool. We're going to say that Y at TI is just going to be YI. And similarly, the state at some time TI is just going to be XI, just to save some time. Okay, so here's the situation. We want to we want to estimate the state X at a particular time. We can map the states at different times to states at a common time. Using, drum roll please, those of you that have taken systems analysis techniques or any fancy controls courses will definitely have seen this before. Using the state transition matrix, or STM. So the state transition matrix, what the heck does that mean? So those of you that have not seen this before, or those of you who saw this before and were confused by it, let me explain what I mean. The state transition matrix. Okay? If we have an ordinary differential equation, if we have an ODE of the form x dot is equal to fx, then we know it has a solution of the form x of t is equal to phi, or phi, depending on your preferred pronunciation, phi t comma t naught x of t naught, where here's what we're going to say. So there's two arguments. There's two kind of almost like function calls, or two kind of function arguments of phi. I'm going to read this as from t naught to t. That's the idea. From t naught to t. And don't be confused by the fact that t naught and the word 2 appear right next to each other and look identical. That's not confusing at all. We're not going to be confused by that. So what I'm saying is phi t naught, or phi t naught, is mapping, like we read this right to left, right? So this t naught matches this t naught, and then this t matches this t. That's the idea that we're going for. And delete that. Okay. So in this equation, oh, hang on. My notes are getting all shifted around here. Bear with me. And we're almost done for the day. I realize we've accomplished a lot, so we're going to wrap up pretty soon. In this equation, phi, capital phi, is the state transition matrix. Okay, which has some useful properties. So this first one might be obvious. First of all, it's a matrix, right? And it's a matrix that needs to be a square matrix. And it's a matrix that needs to be a square matrix that maps the state onto the state. So it has to be the size of the state. So supposing there are n states, sure, I'll kind of make a note. phi belongs to the real numbers n times n, which is to say it's an n times n matrix, which is a square matrix, where n is the number of states. Phi belongs to the real numbers n times n, so it's an n by n square matrix. Phi from t0 to t0 is nothing, right? You're mapping from the initial time to itself. Well, that ought to just be the identity matrix, which it is. Here's another fun one. Phi dot from t naught to t is equal to f times phi t naught to t. So it's interesting how it has the same relationship that the state does. If the derivative of the state is fx, the derivative of the state transition matrix is f times the state transition matrix. Fascinating. Now, might also be obvious, but let's be clear that phi from ti to tk inverse ought to just be phi from tk to ti. Right? That should make sense intuitively. So inverse is the same as if you just change whether we're going forwards or backwards in time, essentially. And then finally, phi from from ti to tk, there ought to be some kind of multiplicative property to this, right? So if there is some intermediate time j, this is going to make sense when I write it out. So if you have a state transition matrix from time I to time j, and then you have another one that goes from j to k, and you multiply those together, you get from I to k. So hopefully that makes sense. So here comes the neat trick. Okay. Y1 is equal to H1 by T1 TK. So from some time K, which we haven't specified yet, we map that to time 1, multiply it by the the measurement sensitivity matrix. This is how we map from X at some time K to some measurement. Remember, this is new. And this is true all the way down to Ym. So Ym is Hm B from Tk to Tm xk plus the mic. Or in vector form, we get y, our measurement matrix, which these measurements are taken at all different times, is equal to, and this is essentially going to look like this, H1 phi T1 TK. These stack is my point. HM phi TM TK. And we're going to call this whole dang thing H in our future equations, right? So when we go back to, well, here, I'll finish writing the equation. Oh, I apologize. These are not vectors. Sorry, got myself confused. So this is a single scalar noise term applied to this scalar measurement, a single scalar noise term applied to this measurement. When you stack them, you get the new vector. My apologies. So the reason I say this is now H consists of a bunch of different measurement sensitivity matrices, each multiplied by a state transition matrix. You stack those, so it takes a lot of effort to get there. But finally, we have something that looks like what we were used to before. So this is the H. If we mosey back on up to our discussion of MLE, this goes here, and then we can solve that way, essentially. So the hard part of solving a batch estimation problem is finding the state transition matrix. But ultimately, the state transition matrix is a super cool tool, which, I mean, we did not take measurements of the state at time tk. We took measurements of t1, t2, all the way up to tm. We can actually estimate what the state will be in the past before any of the measurements were taken. We can estimate what the state will be in the future after all the measurements were taken. We can measure or estimate the state at any time we want using the state transition matrix to map some states essentially onto each of these measurements, or vice versa. That's the idea. And ultimately, we end up with something that looks like our measurement model from the very beginning of our discussion of estimation theory, y is equal to hx plus nu, even though we're taking these at different times. So you might be thinking, gosh, this state transition matrix sounds pretty nifty. It allows us to do all sorts of cool stuff. How do we find it? And how do we use this? And can we see an example of this? And I will say yes, but you got to come back next time, because I think we've done enough for today. So we're going to stop there. Next lecture, we're going to talk about something called observability, and we are also going to talk about a kind of in-depth example of batch estimation. And with that, you will have absolutely everything that you need to succeed at homework 1. Actually, you're pretty much in good shape to take a solid crack. Like homework 2 homework 2, problem 2, you're absolutely ready. Homework 2, problem 1, you're ready to start. And if you're chomping at the bit to make some good progress over the weekend, you can take a look at the course notes that I posted in the kind of supplemental reading section and kind of skip ahead, kind of, cheat a little bit and see what we're going to talk about next lecture. And I think y'all are in a great position to survive and thrive on homework 2. So I'm going to go ahead and stop the recording, but I will stick around to answer any questions about today's topics or about homework 2. So appreciate y'all. And yeah, class is dismissed. Have a good rest of your night.